So Ramesh, what are we going to learn today?
We're going to look at recursion today. Recursion is a programming tool used in some situations where the problem lends itself to a recursive definition.
But Ramesh, what does that mean?
So in a nutshell, it means a function that calls itself.
Oh.
So obviously that sounds like it can result in some unbounded execution, otherwise known as an infinite loop. So how do we resolve this? So let's take a look at recursion in outside of programming. So you may have heard of the term GNU. GNU stands for GNU is not Unix, which is a recursive definition. It's a recursive definition which alludes to itself, that is, it calls itself. The problem with definitions like this is there is no resolution. That is, we never really answered what GNU is. We just said GNU is not Unix, which refers to itself. It turns out this is okay in languages, in speech.
But Ramesh, what happens if a program calls itself over and over and over again?
Exactly. So in programming, for recursion to work, it needs two things. A, it has to have a self-referential statement, which is, we call it an inductive step. And B, which is very important, is a base case.
So what's a base case?
So a base case is what stops the recursion from running amok. So let's take an example. Recursive definitions are pretty common in math. So let's take a recursive definition from math. You all may have heard of factorial. The factorial of n factorial is defined as n times n minus 1 times n minus 2 times all the way down to 1. There's a recursive definition for this. The recursive definition says n factorial is given by n times n minus 1 factorial. So this is my inductive step. Now obviously if I left it here, then this would be a never-ending recursion, because you could keep going past the 1 and into negative numbers. So we need to terminate this. So the base case here says that 1 factorial is equal to 1. So we can end the recursion. So let's take a look at how this concept translates to programming. So in programming, let's write a program, or a function rather, for doing factorial. So I know that I'm going to call this factorial. This is the function I'm writing. And we know that it's going to take an input. So I'm going to make an input, which is an unsigned long, an input n. And it's going to return an unsigned long. So what we know from the mathematical context is factorial of n equals n times factorial of n minus 1. And we also know the base case, so this is our inductive step, and the base case is factorial of 1 equals 1. So let's translate this into code. So the way I would write the code is I would first take care of the base case. and my base case says if n equals 1, that is what that is calling for. If n equals 1, then I'm just going to return a 1. And if n is not equal to 1, else I could do the else, or if I can just fall through, I'll say else return n times, I'm going to call myself factorial of n minus 1.
Okay, so right there is where you called yourself.
Right
Yeah,
there is
factorial
where I-
called factorial.
Okay.
Is that going to work?
So let's see how this works in principle. We're going to trace this program. So the idea of tracing, so let's trace this. Tracing means we're going to take some instances of calling this. For example, I'm going to call this guy as factorial with an input of, let's say, 4, and see what happens. I'm going to start with factorial 4. So what I'm going to show you is how the call looks like. Each call, remember, when we make a call, we refer to the context or the state of the call. We call it, in programming terms, we call it the activation record. So basically, tracing is nothing but drawing an activation record tree, if you will. So we'll see what that means. Here is our activation record tree. So I'm going to call this with a value of 4, which is a call to this function with n equals 4, where all I'm going to do is I'm going to get to the return statement, which says return 4 times a factorial of 3. So that's the statement I'm looking at. So let's look at what happens. So this is going to result in another call where n equals 3, which is going to result in a statement which says n equals 3 times factorial of 2, which in turn is going to result in, so this guy is going to result in a call with n equals 2, which returns 2 times factorial of 1. At this point, our call is going to result in n equals 1 with a which will hit the base case because n equals 1, which will return a value which is 1. So now let's see what happens. This return is going to basically bring me back to this line, which means that I have a value of 1 now, which is going to bring me back from here to here, which the product 2 times 1 is computed, and I get a value of 2, and that's the return value. So now I'm going to compute this product, which is returned from here to here, which is going to be a value of 6, which is now computed as 4 times 6, which is what is returned to the caller, which is 24. Did I do that right?
Yeah, Ramesh. And any downsides to this? That looks like it's going to work.
So it works, and it works very elegantly. There are some downsides to this. The main thing to remember is an activation record gets its space on the stack. We haven't talked about it, but the stack gets used because every call uses a stack. Now, when the recursion gets very deep, we will start using the stack aggressively, and that's going to both may mean that it's going to use up a lot of space, and it's going to be very time consuming. So the drawback is a large problem which is going to give us a bad performance because we're using a lot of space as well as we're using a lot of time.
So Ramesh, it's important with good engineering to have alternatives. So we could use recursion and iteration, solve a problem in both ways, and then figure out which one works best.
Yes, and just to give you an idea, we looked at how this factorial program functions with different input sizes, using an iterative method and using a recursive method. That is a recursive function versus an iterative function. We find that a simple measurement gave us that when we look at the performance in terms of cycles, we find out that the iterative method takes around 11 cycles for an input of 1, whereas the recursive method looks very nice. It takes only 9 cycles.
Ooh, better.
And then we go to 2, and this guy takes 18 cycles, and this one jumps to 23.
That's about the same.
And then we realize that as we go up, 3 takes 25 cycles, this one takes 37 cycles. And it's already beginning to show in terms of the performance hit. And then it goes to 32 cycles, this one goes to 51 cycles, and by the time even a small problem size of 5, we're already looking at a performance which is double the recursion is almost doubling the performance in terms of cycles. Now these are just measurements. There is no way of calculating this. This is observed in our own measurement. Now this obviously for some arbitrary n, this is going to be some value which might, and if this takes Tn and this takes Rn, we have to ask ourselves how do these two compare against each other, and then we decide whether this is within the margins that we need or do we have to choose a iterative method.
Yeah, so in summary, which method is better will depend on both the problem we're trying to solve as well as the input itself.
Exactly.
All right, so what should we do with it now, Ramesh?
So let's take this idea and apply it to a problem we've previously covered. The problem that we've covered is a conversion from decimal to ASCII.
So this is where we're printing out a number on the display.
Yeah. So if I have a number, for example, if the number is 3275 and n has this number, I want to print it out to the screen as the digit 5, followed by the digit 7, followed by the digit 2, followed by the digit 5. So each of these is going to come out of a call to a function called outCar. And outCar prints a single character, and it takes a ASCII input, which is a car. So we're going to use our idea of recursion to write a recursive method to do this. So here's outDec, which is recursive in nature. So it doesn't return anything because all we're doing here is printing it out to the screen. So it takes an unsigned long as our input n, and we're going to go through the motions of printing it out. So as we looked at when we're writing recursion, we first take care of the base case. So my base case,
because you don't want it to crash.
yes, so take care of the important business first. So we say if n is less than 10, which means that it's going to be one of the characters 0 through 9, one of the digits 0 through 9, and we can just print it because there's nothing to do. If n is less than 10, then I'm going to print, so I'm going to call out car, and turns out what I need to do is take the n and add a value which is 0x30, which is basically the offset in the ASCII table. So this is our ASCII table offset where numbers start. And once we do that, we have our base case. Now if we come out of our base case,
That means we're in an inductive step.
then we're in the inductive step. Our inductive step is call out deck, call yourself, and get, but call yourself by eliminating that one digit that you already have extracted. The one digit that I extracted, so the one digit I extracted will be, so the current digit can be extracted by doing n mod 10. So we know what the current digit is, and so we'll make a note of that, but we're going to call ourselves with the remaining of the digits that we want to do, and so we're going to call out car and with a n mod 10, which gives us a digit, and then again we need to add the offset, which is 30. Make a note that it's important that the order, that we keep this order. So John, what do you think happens if I were to swap the order?
Yeah, if you swap the order, I guess 3, 2, 7, 5 would have been outputted as 5, 7, 3, 2, 2, 3.
Yeah, because what we're going to do, what we'll end up doing is we will extract a digit, the least significant digit in this case, and we will immediately print it rather than wait for the recursion to work its way backwards and print this digit first and print this digit last.
Perfect.
And that's exactly what we accomplish by keeping that order. Okay, so so I would urge all of you to kind of work out the activation tree, and if you pause here and do that and come back and take a look at what the activation tree looks like that we are going to show you. So I start with my out deck being called with the number n, which is 3275, which is going to result in n being 3275. So this is the inductive step. So I'm going to first compute, I'm going to call out deck, but I'm going to call it with n mod, so n with divided by 10, which is going to be 327. And I know that I have a statement outside of it, but I only come to this once the recursion ends, and this is going to be an n with a mod of 10, which is basically the digit 5. So let's go through the motions. So I'm going to call this, which is in turn going to call with an n value of 327, which is an out deck with I'm not going to do the math anymore, I'm just going to do 32, and out car with a 7, which is then going to result in another call with n equals 32, which means I'm going to call out deck with a value of 3 and an out car with a value of 2, which now is going to result in a call with n equals 3, which is basically our base case, which means that I'm going to simply print it only has an out car of 3. So what I'll see on my screen,
Which one happens first?
all right, so what will I see on the screen? I will see the number 3 on the screen because that's what that guy does. And so once I do that, the control is going to return back to this line because that's where I am. And so this line executes now. And so I get a 2 out. So that's what the 2 is going to give me. And then again, this ends. So once this one ends, control is going to go back to this line, and this guy executes, and he's going to put a 7 out.
You're brilliant. Look at that.
This guy then terminates, he comes back, control comes back here, this executes, and as a result of this execution, I'm going to get a 5 here.
Wow. Nice work.
So let's summarize what we've learned. We've learned that recursion is a tool which is an alternative for an iterative solution to problems. And in order for recursion to work, we need two things. The first thing is a inductive step, and the second thing is a base case. And any problem that we look at can, if it is properly formulated, can lend itself to recursion. We've looked at a case where there's only one call to recursion. You will see in the literature, and if you look online, you'll find recursion used everywhere. For example, Fibonacci numbers make 2 recursive calls. A lot of tree traversal algorithms that you might come across will basically be recursive in nature. So go on and explore recursion because it's a pretty cool tool.